So we're at the end of the day, the last tutorial. I'm sure, especially for those who have been here for all of them, you probably will during that. So feel free to interrupt and ask questions so that we can sort of circumvent that issue. So I'm going to be describing some of the things we can do with this technique of resonance rate scattering. And my interest in the technique comes from my research where I study topological materials, but also a lot of unconventional superconductors, like fermions which have these very complex phase diagrams with various orders and degrees of freedom. And the power of the resonance rate scattering technique is that it can really be sensitive to all those degrees of freedom. Okay? And in many measurements, the hope is that you can also see how those degrees of freedom interact, how they might couple. So, by tomorrow, you don't remember anything. Hopefully, you still remember that some key facts. Okay. So, one, I think probably the most important one is that resonance rate scattering proves the behavior of electrons and energy. Okay. It proves local and collective behavior and many degrees of freedom. Spin, charge, lattice, all of those. And that this is all possible because of this resonant condition, which brings you to that enhances an otherwise small second order term of perturbation of the scattering cross section. Okay, so the resonance is the key thing here. Basic things about how resonance rate scattering works are performed as synchrotron facilities. In order to tune to these specific photon energy resonances, you need to have a tunable source of photons. This technique is also incredibly photon hungry, so you need to have really brilliant light sources, and so you really have to do these synchrotron facilities. Okay. Depending on the complexity of the resonance X-ray scattering experiment, you can have larger and larger degrees of complexity on how the experiment is done. I sort of divide them into three kinds here. What are called energy integrated resonance X-ray scattering. Also resonant inelastic X-ray scattering rates, which is probably one of the ones you see the most around. And now the ability to do some, especially in the soft X-ray regime, colorimetric resonant X-ray scattering, where you resolve the polarization of the outcome photons. Okay? And in doing all this, you can learn more and more about the excitations in your system. Now, I don't have a highly linearly structured talk. I will start by showing you several examples that relate to my own research of how experiments can probe these different degrees of freedom. And hopefully, you'll see something that might interest you to apply to your own research, or maybe you can see resonance X-ray scattering as a technique that might give you some opportunity to solve your own scientific questions. If you have an idea, look for your local scattering experts, talk to beamline scientists, or if you just want to send me an email or find me as I'm going to be here throughout the week on and off, so feel free to just pull me aside and discuss some ideas. Okay. I should emphasize that resonance X-ray scattering has been a very, over the last years, it has really been developing technologically. Okay, very exciting in that sense. More and more, high-profile experiments being done with this technique. But I think we're only really hitting the surface of what we can measure, okay? Partially because on one side, technologically, we're not, we're always improving. Another side of this is just that we don't quite fully understand what's going on. Okay, so there's a lot of, I'll make an appeal to theorists who want to go deeper into this technique. So I will start by giving my simplest possible introduction to resonant X-ray scattering, and then I'll show you a few examples of the first one of charge density waves with the loop rates, the second one showing that we can measure a magnetic peak on the material I've been studying recently, using voltage 5, and on the third example, I'll discuss a very acute experiment on strontium glutamate, 3 doped with manganese. Okay? And then after these examples, I'll go a little bit into some of the basic theory. I'm not going to derive all these things, but just to give you an idea where things come from. Talk a little bit about practical things and how to do experiments. And then I'll finish with examples of rigs and polarimetric rigs on data that we think shows an interesting coupling between charge and magnetic degree of freedom. So as I was saying, technology-wise, okay, there's been a lot of development. If you look at a rig spectrum, so I'm doing this in elastic wave, and looking at the spectrum of excitations of an antiferromagnet, a unducted lithium copper oxide. And you can see that in 1996, with an energy resolution of 1.6 electron volts, you have a very broad spectrum. You can't really learn anything about the system there. By the time John Munger and Gavin, Richard Brojkovic started making better and better instruments, you can see here, but by the time you have a 0.8 electron volts resolution, you can see that the big blob is actually 2 peaks, okay? And by the time you push the resolution, this started in 2008, to 130 milli-electron volts at the axis pin line, you can see that actually that big blob is at least 4 peaks. And the peak that might interest you here is the second peak, okay? So you have the elastic line, and then you have this other guy here, okay? And this other guy turns out is a magnet, okay? Just showing you that you can get a spin flip process out of the resonant X-ray scattering process, okay? So let me show you this in more detail here. If you compare it to neutron scattering data, okay, and you go to the same wave vector, which is around here, 1/2 0, you see the energy is around 300 electron volts. When you look at the spectrum at the same Q for a Riggs experiment, you can see that it's also around, near 300 millivolts. Okay, and then if you make a comparison between the two, in this paper, 2010, it was shown that actually you get you can see the magnet dispersion both perfectly agreed. Okay. Of course, you might ask why. Yes.
You see something continuum also?
Yeah.
And is it more sensitive to the continuum than the neutron, or less sensitive?
No.
Compared to the peak?
So, I think it's going to be more sensitive. Yeah. But that will depend on where the magnetism is coming from. It's depending on which direction you set yourself to. But then, so the question I was posing is, why do this? Why do they want to do resonant X-ray scattering instead of doing inelastic neutron scattering? Right? And there is a very practical reason for this, which is sample size. Okay? So for that kind of quality data, neutron data, the proof rates you may have to ask your students to grow 100 different crystals and co-orient them on some sample holder and make sure that it's all aligned, and that student will be, well, I suppose highly frustrated, but eventually is going to get this done and get some nice neutron data. Okay? The kind of resonant elastic X-ray data that can give you the same dispersion, already, with not the same energy resolution that you can get from neutron scattering, you can do on really tiny samples. Okay? So a typical spot size of this kind of Griggs experiment is going to be 7 by 60 micrometers. It's going to be small. Okay? So as long as your sample area is going to be larger than that, you're going to be able to get a very large signal. Okay? So the equivalent for Ritz would be then these little black speckles here. These are the samples that are being measured. All right, so additionally, I told you about 130 milliamp resolution. Really the best limit right now is at the Griggs instrument at the European Synchrotron Radiation Facility, where they achieve energy resolutions, if you really push it, around 30 millielectron volts. Okay? And then there's a similar instrument at NSLS2 at Brookhaven, which is coming online and maybe is on the verge or has just achieved similar kinds of resolution as well. I'll show that a little bit later. So, typical problem, what does resonant phase scattering measure? If you, as I did a couple of years ago, but you can just go on the archive and you can look and you see titles that talk about magnetic excitations, spin orbit excitons. You're looking at superlattices, okay? You can look at thin films and things like that. You can be looking at electron cloaking coupling, presumably, and also superconducting pairing, or charge and spin excitations, or even the band structure. Okay? So everyone has a proposal, and there are many measurements that show that, in different regimes and different samples, you can be sensitive to these. Okay, so you read the resonant X-ray scattering paper, and it looks like the typical blurb that I've been repeating: lattice, spin, orbital, and charge degrees of freedom, which in essence means that you can measure phonons, transitions between orbitals, magnets, drawing, and so on, okay, and band structure. Now, of course, when you look at a different kind of experiment, I do a lot of SCM, for example, and so I can just, if I don't, zero order, I can start my papers by saying, we measure the local density of states and move on. Maybe if you're doing a neutron measurement, you can extract the dynamic magnetic susceptibility and so on, you're fine, right? And the reason you can say this is because a lot of times you can manipulate, you can present your technique in terms of linear response theory, okay? Where you have a probe, you have an interesting system that you're trying to probe, okay? And as you, hammer that system and excite it, that system is going to react. You're going to hit something, and you're going to make that detection. And if your measured response is just going to be equal to, if your measured response is proportional to the probe, that proportionality is the susceptibility, which tells you something about the system. Resonant X-ray scattering is definitely not that. Okay? It has a complicated expression for its cross-section. Okay? And any manipulations that you try to do to write it in terms of a density correlation function or something like that is ultimately going to involve some kind of approximation that is terrible. So I recommend just not trying to do that. It's just going to induce you to some kind of error. On the other hand, this complication is actually the beauty of the technique, okay? Because that is what allows you to study all these degrees of freedom, their couplings. Okay? If you want to study the coupling between these degrees of freedom, you need to be able to grow all those degrees of freedom. Now, how those sensitivities are going to happen, there's no general formalism for that, right? You're going to have to think about your material as well. Maybe you're going to have to find a theorist and say, I have this data, I don't understand, can you do some simulations and try to figure out if I'm measuring charge or spin, okay? But I think the technique gives you so many beautiful things and data that shouldn't stop you from doing the experiment. You should do the experiment first and then ask questions later. Okay? So, my quick and dirty introduction to resonance ray scattering is the following. Okay, it's going to emphasize one aspect of it, the resonance. If you want to probe structure, periodic structure, the electronic properties of the material, of course, if you're thinking about charge, X-rays come to mind. And typically, you're going to be thinking about doing a hard X-ray experiment, which is going to be in the range of 10 to 100 kilo electron volts. And at those energies, unless you happen to hit a resonance, you're going to be sensitive to basically all the electrons of your material. Right? Some of the materials we study are very complicated, have many atoms per unit cell, and many electrons. Also, most of the electrons are really much closer to the nucleus. Only the valence electrons are out there. Okay, so you can essentially think, if you're probing mostly all the electrons that are in the nuclei, you can think of your atoms in your crystal structure as little points, and you can essentially think of this basic scheme that you learn on the Mandel's needs about Bragg scattering. Just to say that this is a great probe structure. Okay. But there might be a situation where instead you want to measure one specific electronic state related to one specific orbital of one specific atom in the sea of all those electrons. Okay? And then you have to use resonance X-ray scattering, and then the way it helps you to basically just quantum mechanics. Okay? So what are you going to do? You're going to find a particular resonance. What I mean by that is that, for example, for copper, you will find that at roughly 932 electron volts, that's the energy separation between a typical core 2p electron and an unoccupied copper 3d state. And that unoccupied state, of course, is right next to the Fermi energy if this thing is roughly an element. Now, you find this resonance by looking at the absorption spectrum. As you tune the photon energy in your synchrotron experiment, you measure the X-ray absorption, and at the point where you see the full absorption, you know that you hit that resonance. Okay, so the resonance really looks like a resonance. And then it goes through this intermediate state, okay, where you have that electron sort of feeling out what's happening near the Fermi energy, and it left a core hole behind. And then it decays and the photon's emitted, and now you have a photon in, photon out technique, so you can do scattering at that resonance condition. So this resonance, which shows a specific element, right? Copper is going to look like copper with resonance second. Any copper, regardless of the material, is roughly going to look the same. And in this intermediate process, because of the core hole, you're really stuck to measuring this copper atom. But you're also sensitive to these intermediate electronic states of the particular element you chose. And so, people will say this is a technique that's sensitive to those valence electrons through these intermediate states. Okay? The challenge is then to understand what sensitive to these intermediate states actually means. So, let me show you an example. Okay. And let me really show you with pictures. So, my example here is a this is something that got really hot a few years ago, 6 years ago, and it's been like, 50 or more papers on resonant X-ray scattering, on cuprates. But let me start by showing you some SCM pictures. Okay, so this is a topographic image of a typical bismuth-based cuprates, where you have the little dots there. Okay, those are forming a square lattice. These are the small ones, and those are just the distance. They're representing the square lattice of the column. Okay. And then you have these squiggly lines there, and those squiggly lines are another structural distortion that happens in these materials. So really, you're looking at the structure. This is a topographic image from SCM. This is telling you where the atoms are. But if I look at the density of states, the local density of states of this material, just above the Fermi level. Okay, so 25 millielectron volts above the Fermi level. This doesn't happen at 50, and it's going to be very suppressed even at 0. Okay, but at 25, you're going to see that on the same area, you can hardly see some of the structure anymore. And really what you see is this otherwise checkerboard order. Okay? And just to highlight what you're, this checkerboard you see here, sort of the basic unit of the checkerboard is this blinking yellow square. Okay? And so this is telling you how the states at 25 millielectron volts are self-organizing. Okay? And of course, these are states that are, you know, something about the cuprates is related to the hybridization between copper 3D, X squared minus Y squared, and oxygen to PX, oxygen to P pi. That's real space. Of course, you can always, it's a scattering technique, so we want to look for things in Fourier space. So if you just take a Fourier transform of that data, you see peaks, which is just to help you translate between real space and reciprocal space. Okay? So the center here is cubical 0. The peaks related, the Bragg peaks are on the corner of the image. These peaks are near 0.25 reciprocal lattice units, which is a quarter of the distance from the center to the corner. Means things are periodic at the 4 lattice constants. And so, are we going to use hard X-rays? No, right? Because then you have to vary out one single electronic state out of everything else. You may want to use resonant X-ray scattering, right? And here, as I said, the energy states here, the Fermi energy, they also have some oxygen character. So you could have equally chosen, instead of a copper L edge, you could have chosen an oxygen edge to help you enhance those states. And you can do it. It's just, for technical reasons and because you need some energy to have, to fit the geometry of the scattering, and it's easier to do it with copper. Okay. So once you constrain the energy, you can work with your scattering geometry, and you can look for that orderly. Now, this is where I say the easiest experiment you can do is the energy integrated, as I call it, resonant X-ray scattering. This is not really a standard term, but I'm hoping to make it standard. Because what you're doing here is that you have an incoming beam scattered off your sample, and if you detect all those scattered photons in your detector, regardless of whether the photon went through an elastic process or whether it lost, 1 electron volt, you count them equally. Okay? So I try to call this energy integrated resonant X-ray scattering because in the literature you will often find it called a resonant elastic X-ray scattering, which is not true. If you want to do a resonant elastic X-ray scattering, you have to do a resonant inelastic X-ray scattering and measure the elastic line. So elastic and inelastic scattering processes are counted equally here. Okay, so we look at, now I just jump between cuprates, but basically the story is the same. I'm looking at an electron volt cuprate in this case, because I have a better slide for this. And as when you tune the photon energy to the resonance, you measure through reciprocal space, you see a peak, okay? And this is a very, looks like a very tiny, weak peak, okay? If you look at the signal, is roughly less than 1% of your background signal, whereas if you were measuring, say, a Bragg peak, that would be a million times your background signal, okay? But if you go off resonance by just moving the photon energy, half of you one way or the other, then the peak is gone. Okay, so this is really teaching you that it's through that, sensitivity to the intermediate states that you can really see this kind of ordered state. And through that, you know that it's coming from those electronic states related to the Kaltbronx outline. Things that have been done in the recuperates, being used a lot in many papers and so on. So that example shows you that the resonance can really bring out really small signals. Okay? And that was an example of charge. Okay? But this technique can also measure magnetic peaks. So here's this, we're starting to study this neodymium cobalt-1 5, which is has a magnetic ground state. It's in the series of these 115 hanging fermion, typically superconducting materials. But just to give you an example of an honest to God strong peak, okay? And a magnetic one too. All right. So here I'm on a log scale, okay, and this thing orders in a magnetic structure that's stripe-like. With a wave vector and reciprocal F, units at 0.5, 0.5. Okay, so only along one direction, not the other. And if you go below the transition temperature, Nel temperature here is 8.5 Kelvin or so. If you go really low, at 4 Kelvin, you can see that the peak is very large, very sharp, and close to the intensity you'd expect from a Bragg peak. And it shows a beautiful mean field-like order parameter behavior. One thing that does happen, though, that might be hinting you about the fact that this actually creates an integrated experiment, is that if I go above the transition temperature, okay, even as I go 9, 10, 11, 12, 13 Kelvin, several Kelvin above the transition, you can still detect the peak, okay? And, really we're measuring it now in this region here where this plot actually telling you those things. But the enhancement, if you go off resonance, you're not going to see this, but the resonance enhancement is so large that it's allowing you to detect things even above the transition temperature. And this kind of diffuse scattering, because you're in energy integrated mode, can either be coming from, inelastic and inelastic signal, to be dynamic correlations, if you will, or it's coming because those dynamic, or because the correlations are very short range, and you're really getting diffuse scattering. In either case, yes. K is the second axis in the reciprocal lattice unit, right? So I could write the peak as H, K, and L, and in this case, the order is around 0.5, 0, 0.5. So if I sit there and I scan this axis, that's where I'm scanning there, from negative to positive. Yeah, so that's the direction of that cut there. But depending on the geometry, you can take a cut along in the other direction. So you're still sensitive to even small portions of shortly correlated orders above the transition. Let me this case here, there's a non-structural distortion that happens around 60 Kelvin. Okay? And as you go below 60 Kelvin, this peak here, H equals 1/4, K equals 1/4, L equals 0, appears. Okay, so the structure changes. And here, you could, of course, if you're just looking at fluid strength ruthenate, you just have to use the ruthenium edge to amplify my signals. The electronic states are going to be related to the ruthenium oxide, so that's a great choice of edge. And as you do this, you can. This is the absorption on the left. Here on the right is the energy profile of this peak. You can see that it also peaks on resonance, and you can see the temperature dependence of the peak, and it shows the behavior you would expect. Okay? But now, the idea is what happens if I remove the ruthenium and substitute some manganese, and then decide to use the manganese edge instead. Okay? Sort of use the manganese as like, an infiltrated probe of the environment where the ruthenium oxide is. And in that case, if you do that substitution, in this paper they measured with 10% manganese, you can see that at 60 Kelvin, with the 10% manganese, well, they detect a peak at low temperature. And it has the same temperature dependence, more or less, of the measurement of the ruthenium. Okay? And at 10%, it's okay, because at 10%, the average distance between the different manganese is going to be comparable to the correlation lengths that quickly develop inside the ordered state. So you get a coinciding transition temperature here. If instead you choose 5% manganese, it takes a little longer. You have to cool it down a little more before those, dilute manganese atoms can actually feel the correlation length of the order come in. Okay. So this is to say that, one, if you don't have the appropriate edge to do your experiment, you can always go to your local synthesis person, and that's Valentine, and ask to put some impurities in it. And you can, maybe the dopants that you put in are going to be located in a place where you're going to be sensitive. You're going to insert it in the matrix that you're interested in, and you can use that as a probe for your resonance X-ray. Okay? And that same thing, you can also say that resonance X-ray scattering because of the site selectivity through the resonance is really also a local probe in the same way that NMR or electron spin resonance, etc. are. Okay. So this is that was the third example. Okay. And but now I'll say a little bit about some useful things about scattering that might come in handy. Okay. Now I'm not going to talk about, everyone has a bachelor's in physics knows how to treat electromagnetic radiation, Maxwell's equation, and so on. And you probably know how to derive the expression for differential cross-section based on the influx of incoming photons and the flux of scattered photons that you measure. Okay? These are standard textbooks paints. And you can arrive at expressions for the scattering of an electromagnetic wave through an electron and so on. Okay. And I think, are we posting things? Are we providing the slides? Are we providing the slides? I'm not going to go through detailed equations, but if you want to look at it so that you have an idea, be glad to provide the slides later. Now, it's important to talk about structure factors a little bit. So in drag diffraction, we're basically treating the interference interference between point charges, right? But really, an atom is not a point charge. It has a density cloud, a cloud of electron density. And you're really interested in the interference, that you picked up here is this extra, length, okay? And as long as this length gets you over by a, full 2 pi, you get constructed interference. So this is basically mechanics. But for this, you have to take your atom and you have to really integrate over all the charge density in your atom and take into account the interference between not only 2-point charges but the charge located everywhere. Okay? So that's your atomic structure factor. Okay? It takes into account the interference between all the charges in your atom. If you move on to having multiple atoms in a unit cell and then going over multiple unit cells, you have to sum up first over all the form factors inside a single unit cell, and then summing over all the form factors over all the unit cells. And so you get the form factor for the crystal, reminding you that you have these lattice phase factors. And so whenever, for a crystal structure like this, whenever Q dots with the basis factors 2 pi times an integer, you get the Q equals G condition and you get rare Qs. Practical things, that's if you end up thinking about doing an experiment and you're just trying to figure out how to calculate Q, you have an incoming photon with wave vector k, and if you want to determine that Q here, which is the Q that if you tune to a reciprocal lattice vector is going to be the direct peak, you have to move your detector to some other angle, and then the subtraction of one wave vector by the other gives you the Q. Okay? And to tell you, in case you don't know some jargon about this X-ray scanning experiments, the detector angle in relation to the incoming beam is called the 2 theta angle, which is not 2 times theta, it's just called 2 theta. And that detector angle is going to determine your Q. Once you have that determined, you want to project that Q onto your sample, and so you may want to rotate your sample. If you're in a way in which you rotate your sample and now this Q is aligned along the a-axis of the sample, you can measure the peak along the h00 direction. Okay? And this is called the transmission geometry. In many cases, resonance conditions you're interested in might be the soft X-rays, where the photons can't go through the sample, okay? And then you have to work in reflection geometry. Okay? So in this case, you have a geometry where you're throwing peaks along 0, 0, L, but also some mixture of H and L or K and L. Polarizations, depending on how you want the light to couple to the orbitals you're interested in, you may want to take into account the polarization. So if the polarization is in the scattering plane, then this is called pi scattering, and if it's orthogonal to the scattering plane, this is going to be sigma scattering. So just some practicalities in case you're reading papers. Okay, so the equation where everything comes from is this Kramers-Heisenberg equation, okay? It's Kramers and it's Heisenberg, so this is 1932. Okay, the quantum mechanics here is not too hard. And it ends up with 2 terms here. The first one's going to be the Thomson scattering term, and the second one's the second order term, which is going to give you the resonance. Now, I'm not going to go through the derivation, but I just want to point out, because I think it's important that if you're going to do an experiment like this, maybe take some time to look over how you get there. Or if you're a theorist, maybe you can do this in knowledge, I don't know. But basically, you're going to have a Hamiltonian, and you're going to spread your Hamiltonian out into the electron, the Okay, so this is quantum mechanics. First year graduate students know or are learning. And you have the interaction Hamiltonian. You know how your quantized field is. You know, you can basically open Zacharias quantum mechanics and see how this works. Okay? And you basically want to know the probability that if you start the system in a state where you have a photon in K and the system is in A, you go to a photon in K prime and the system is in B. Okay? And if A is equal to B, that's a biasing scatter, and if A is equal to B, that's going to be no less. You can do your typical perturbation theory, get the second order perturbation terms, okay? Apply density of states, etc. Go to your to calculate your differential cross section for the scattering. And my point here is that this is, you know, I find it remarkable the amount of people who do the experiments but actually never went through the trouble of deriving that. So I recommend that if you're going to do an experiment like that, you should take a day to go through the derivation. The sum of this, you know, the summary is that the first term, the first order term, is going to be Thomson scattering. Light comes in, light comes out. Okay? The second term is the resonant term. Okay? Where now the light comes in, you go through the intermediate states, you come back down, light comes out. Okay? So you see here, you start at A, you go through some interaction, you take your system to the intermediate states, you go back to B, you emit the photon. Okay? The term in the denominator here is what gives you the resonant condition. So when the photon energy is equal to h bar omega, and only when the photon energy is equal, only when h bar omega is near En minus Ea, the resonant condition, is this term going to be infinite. Okay? Otherwise, this term is going to dominate. But when this is diverging, you can forget about the Thomson scattering mostly, and then you can basically just concentrate on this second order resonant term. Sorry? A and B, not necessarily, right? If you do an inelastic experiment, if you're looking at an inelastic scattering, you start at A, but you leave your system inside it. So A is going to be different than B. If it's the elastic part, A is going to be equal to B. Should mention though that there are funny things that can happen because these, let's call them the Thomson form factor and the that's an X-ray form factor. Once you put all those form factor things in, they can, it's not the summation of the magnitude of both. It's actually, there's an interference between them. And so there's that additional complication, but I'm not going to go into this. Okay, so how things may come in. Well, if you have a system that dimerizes, a classic case of a Pyros distortion, where you have your two photons, your two atoms sort of start to dimerize in a lattice that was otherwise periodic every A, okay? Then you can write those lattice positions as Rn equals Na plus some perturbation on it, which can be, you know, your CDW, your cosine QCW or other periodic structure. And once you put that into the structure factor, you can get the condition that you require that Q is going to be some number of times pi, 2 pi over A, plus or minus Q CDW. You're going to see CDW peaks that are set aligned to your gravity peaks and so on. Okay? And this kind of structural distortion doesn't require the resonant condition. Okay? Because in this, I could have worked this out in the Thomson scattering of the model. Okay? Which is typically what the hard X-ray scattering is going to look like. But if instead, okay, now let's say that what my periodic modulation actually is an electronic modulation. Okay? Maybe my electronic states, as I go from one lattice position to the other, they change their valence. Okay, they change their energy level. And if they change their energy level, that means they're going to affect this term here, En minus Ea, but not, your Thomson scattering. Okay. You could also have things that are modulating, your matrix elements itself, which are also, modulations of those end states are not going to be present in your Thomson scattering. Okay. So if your valence itself is modulating, you can write this energy difference as an average valence plus some modulation of that valence, and you can sort of work that out, and if that's small, you can bring it out to the exponentials, and you're still going to get a peak. But this stuff only shows up on resonance. Okay? So this explains to you why, for example, in the Coupe's you have to go on resonance for the case of that I showed to really see the charts. Okay, so the beginning of the experiment is actually the X-ray absorption. Okay, and so when everything is failing, you stop and you say, okay, let's go to the beginning and take X-ray absorptions. Line. And then the X-ray absorption by itself, which is the beginning of the experiment, is already a very powerful technique and hard, and it goes into this matrix of 4-level spectroscopy of solids. Okay? And so this is just to mention to you that you have to be careful if you are going into resonances that are not simple. Copper L3 happens to be an easy one, so the way these resonances are indexed is that if your initial state is an n equals 1 state, that's a k edge. If your initial state is an n equals 2 edge, n equals 2 state, that's an L edge. If it's n equals 3n, and so on. Okay. And really, you have to be careful because you're making a transition from maybe like, creating a core hole in an otherwise full shell, and then creating a core hole there, and then going and adding an electron to another shell that was otherwise open. And so there are lots of things you have to take into account here, Hund's rules and so on, etc. And if you're not on a copper edge, things can get complicated. So let me just jump here to, what if you look at cerium 3 at cerium, or cerium at different, cerium 2 plus, 3 plus, 4 plus, and so on. In some cases, there can be, hundreds of transitions, and so you might not be exactly sure what electronic state you're looking at. Okay? But you shouldn't let those complications bother you. You should really just, if you have an interesting system and you know that, it's the atom you're interested in, you should just go ahead and do the experiment. Okay? And the practical way in which you do it is that you look for the edge. Okay? If you've been at synchrotrons, you've seen the X-ray data booklet. What's the energy of the edge that you're interested in? Let's say I'm interested in the F electrons of cerium, but I'm going to be looking for the M edge. You look around on the internet to find out if that has been measured. You look for an instrument that lets you measure that photon regime and maybe contact your expert or beamline scientist. Okay? The energy of these edges, if you're interested in transition metals and 3Ds and 4Ds, they're mostly going to be in the soft X-rays. If you go to 5Ds, they're going to be higher in the hard X-rays. And that significantly changes what kind of synchrotrons you go to, or because the difference between soft X-ray instruments and hard X-ray instruments is very large. For soft X-rays, you're going to have to do things in vacuum. For the hard X-rays, you can do with different spectrometers and instrumentations. Okay, so let me then tell you a little bit about magnums and cuprates. Or in the case of doped cuprates, where The ground state is not magnetic, but magnetic fluctuations are still around. These are called paramagnets. And this is going to, and this will highlight some of the best sort of instrumental resolutions of capabilities that are available right now. So far I was talking about energy integrated resin X-ray scatter, but now if instead of collecting all those photons, I do the basic spectroscopy. This is not quite the prism and the candle experiment, but the principle is similar. I'm going to take those photons and I'm going to put it through a spectrometer that spreads them out spatially depending on their frequency or energy, okay? And then I'm going to image them on a flat detector, and depending on the line where I see, I know that it's a scattering photon of different energies. Okay? And then we're going to see all these beautiful various photon magnons due to the excitation and so on. Okay? Now, if you want to do this well, what you want to do is to be able to spread out these lines as much as possible, so that means the longer I put my detector away from that point where I spread the lines, the better resolution I'm going to get. Okay? So what they did at the SRF beamline then was to make basically figure out the technology necessary to make a very long arm. Okay? So that's what I show the video. Okay, so that's the detector arm there. It's about 12 meters long. Okay, the sample is some millimeter thing here. The light gets scattered, goes through the spectrometer, spreads out the lines, and then you collect them with CCD cameras that are out here. And you have to be able to do this while having a motion of a large degree of angular motion, while maintaining without breaking the general direction. And this detector, you have to be able to do it in many different ways, but specific precision in the micrometers and so on. So this, that was a little loud. Although my computer said it was muted. But that instrument is really the state of the art now, although there is a very similar instrument being put together already, starting to be operational at Brookhaven. And that's the one that gives you the best energy resolution. So the progression of the technology for these instruments is just been increasing at a very rapid rate. And that's probably one of the most difficult beamlines right now to get beam time. Now, we did get some beam time to work on looking at the electron doped loop rates. Okay? So the way we do this experiment now is that for each point in reciprocal space, I'm taking a cut here along H, okay, the first direction of reciprocal space. For each point there, you take the spectrum, okay, so these are spectra for different H values, and you can see their peaks, and their peaks are moving around and things like that, okay. And if I put them all together in a color plot, and the intensities are different, but you have things that are known to be dB excitations, where you go from one d orbital to the next. You have the elastic line down here. You have the paramagnons, which look broad, but it's not because of the instrument in this scenario, it's just because they're intrinsically in the doped system, so it's not very ordered. There is even a little tiny peak here that you can resolve near the elastic line. Okay? And that's what it is, but it's not really formal. So to make the connection to the energy integrated measurement, because this is a point people miss a lot, if I integrate this over energy, then I get a line that's amplitude intensity versus momentum, and that's the line that I end up with. Okay, so that's the connection between the two kind of experiments. And there you see the attributed charge density wave. Now, I would say what I'm going to show here is that the limit of what the instrument can tell you, at 300 Kelvin, you see the paramagnum dispersion here. Okay, I didn't fit this, but it roughly has this form. But when you go to 25 Kelvin, you see the paramagnum dispersion. Here's that finger, I think is the form here. Here's the paramagnum dispersion at 25 Kelvin. And if you measure, this is like roughly 4 or 5 days worth of data. If you really push the instruments, what you get is that you see small modifications, but resolvable modifications to your paramagnum dispersion. It seems like there might be some change in dispersion, some additional intensity there, some increased intensity on top of the paramagnum. And the funny thing is that this is all happening at the charge density wave vector, where you would see a charge density wave on the elastic line. Okay. So, look like the charge density wave somehow is affecting the paramagnum dispersion. Okay? And that's really the beauty of the experiment, that you can sort of measure these different things at the same time. So, to test this, okay, to take a map like this, we use the 50 millimeter resolution to get a little more intensity. But if we just focus on one particular wave vector there, and compare it to one that's off the charge order, you can see that there is indeed an enhancement at the charge order wave vector, the blue spectrum here, right on top of where the paramagnum energies are. Okay? So this is just, the quality of raw data. This is like these two spectra probably took about 12 or 16 hours. Now, to know what's going on here, right, because now it comes to complication. You're measuring, I'm talking about charge order, charge density waves, and paramagnum at the same time. What the hell is this? Is this a spin flip process? Is it magnetic, or is it charge on top of magnetic, etc.? Okay. And to do this, the next level of technology then for this instrument, which has just been developed, and then there's a paper in preparation talking about instrumentation, but it's based on a previous concept, is to have a polarimeter, right? So after you spread out the lines, before you look at the CCD, you put another multi-layer there, and you either measure with the multi-layer that changes the photons to go to another detector, or you let them go and you measure normally. But by putting this element in here, you're changing the ratio of the polarizations of the outcoming photon. Okay, so I set my incoming polarization with the synchrotron, but the scattered photon, typically, so far what I've shown you, I'm not resolving whether it's coming out with linear polarization signal or with pi polarization. Okay. But if I can now measure, then going through, or changing the ratio and measuring otherwise, I can do some linear equations, some linear algebra maybe, and figure out, explicitly measure only the sigma prime channel or sigma pi prime channel. Okay. And the rule of thumb here is the following: is that if you measure, the non-cross channel, sigma to sigma, that is going to be a charge thing. And if you measure the sigma to pi prime, that's going to be a spin flip process. Okay. So we look at the sigma pi prime. The sigma prime doesn't show much, and you can see here that you can beautifully see now the paramagnum dispersion. Okay. And on top of the paramagnum dispersion, there is indeed an increased intensity at the charge order wave vector. Okay? So in addition to the elastic charge order, you also have this component it's spin flip, but is at the charge all the way back and has a temperature dependence of the charge order and so on. Okay? So this is really pushing you to see that there's a coupling between the two. We have a little cartoon picture for what this might be. So if you imagine that you have a charged SUA on top of strong antiferromagnetic correlations, then a fluctuation of that charged SUA and then a two-on or a phase-on is going to necessarily involve the transfer of charge from one atom to the neighbor, and it's going to perhaps force it to have a spin flip. So this data here, that's now a week worth of data, and they're not going to let us do anything more than that. But this shows you that if you really push energy resolution, polarization resolution in a great synchrotron and beamline, you can really start to learn a lot about not only magnetism, but also its coupling to other behavior. So, just a couple of other things that my group has been working on or collaborating with folks that are exciting, and so you should have in mind. One thing we're doing is applying uniaxial strain to samples and measuring these scattering peaks and so on. If you think that there's an application for whatever problem you're scientifically interested in, for doing resonant X-ray scattering in the presence of uniaxial strain, we have a working device and apparatus. Feel free to contact me. And one thing that a lot of people are actually doing is combining resonant X-ray scattering, okay, with ultra-fast optics. Okay, so here is an experiment led by Giacomo Kozlovic, the LCOS, the free electron laser, SLAC. And there, the experiment, we're sending 1.5 eV infrared pump photons to excite your system. Depending on the temperature you can either be in a regime where you're killing superconductivity but not affecting the charge density wave, or affecting the charge density wave because you're not in the superconducting state. And then you can then come with the resonant X-ray at 932 eV, but with femtosecond, tens of femtosecond resolution in time, and sort of look at the dynamics of this, and if looking at this sort of dynamics is something we're interested in, there are also, you should start thinking about these kind of experiments. So, come back to my takeaway messages. Remember, the resonance is king. It allows you to measure not only take out small electronic states out of the sea of all the electrons in your material, but also allows you to measure different degrees of freedom. Depending on what you need, I would consider basically just starting with an energy integrated measurement and then moving on to more complex things. And if you have any ideas of how resonant X-ray scattering could benefit your own research, of course, feel free to talk to specialists or to myself. So I think there's a lot to do with this technique and a lot that's still very unexplored, especially magnetism.